Hi, everyone. Welcome and good evening. My name is Lauren Artilles, and on behalf of Harvard Bookstore, the Harvard University Division of Science, and the Harvard Library, I'm honored to introduce this virtual event with Carlo Rovelli presenting his new book, Helgoland, Making Sense of the Quantum Revolution, in conversation with Katie Mack, with a special introduction by Harvard's own Matteo Mitrano. I hope you're all well and safe. Thank you so much for joining us virtually. Tonight's event is the latest installment in our Harvard Science Book Talk series, which works to bring the authors of recently published science literature to our Cambridge community and beyond. Coming up in the series tomorrow, May 26th at 5 p.m., we'll host acclaimed writer and professor of mathematics Jordan Ellenberg for his new book, Shape, The Hidden Geometry of Information, Biology, Strategy, Democracy, and Everything Else, in conversation with best-selling author and mathematician Kathy O'Neill. To learn more about this and our other upcoming virtual events, you can visit harvard.com and sign up for our email newsletter, or check out the page harvard.com/science for more info. I'll also be posting a link to our Science Research Public Lectures YouTube channel in the chat, where you can view previous talks that you might have missed. This event will have closed captioning available. Depending on the version of Zoom you're using, you may need to enable captions yourself by clicking on the closed caption button on your screen. This evening's discussion will conclude with some time for your questions. So if you have a question for our authors at any time during the talk tonight, click on the Q&A button at the bottom of the screen and we'll get through as many as time allows. In the chat, I'll be posting a link to purchase Helgoland on harvard.com, as well as a link to donate in support of this series and our store. Your purchases and financial contributions make events like tonight's possible and help ensure the future of a landmark independent bookstore. So thank you so much to our partners at Harvard University, and thank you to all of you for showing up and tuning in support of authors, publishers, indie bookselling, and especially for science, because it really, really matters. Finally, as you may have experienced in virtual gatherings all for this last year, technical issues may arise. So if they do, we'll do our best to resolve them as quickly as possible. Thank you for your patience and understanding. Now I'm excited to turn things over to Matteo Mitrano, experimental condensed matter physicist and assistant professor of physics at Harvard. The digital podium is all yours, Matteo.
Thank you, Lauren, for the introduction. Now it will be my turn to introduce our guest tonight. So it is my pleasure to introduce the conversation between two very distinguished guests, Carlo Rovelli and Katie Mack. Carlo Rovelli is a theoretical physicist with a very long career that started in the late 80s after his PhD graduation in Italy, and following several research stints in Rome, in Trieste, and then in the US at Yale. He started serving as faculty at the University of Pittsburgh, and since 2000 at the Centre de Physique Théorique of Aix-Marseille. He's well known in the physics community for his pioneering work in low quantum gravity. And I actually started learning about his research from friends in the University of Rome Sapienza that were also interested in loop quantum gravity, although I work in different research topics. And this work, this pioneering work that he has been performing, is extremely relevant to the unification of the physical description of our universe. His research has been informing a very productive activity as a science communicator. And Carlo, over the years, has been introducing the public to fundamental questions of modern physics, such as the definition of time, space, and observables. A common theme of all these works is the awareness that physics, what physicists do, is intertwined with the human adventure driven by curiosity and ingenuity. And this display that makes this communication, the science communication, particularly effective. He wrote many, many books, such as The Order of Time and the beautiful 7 Brief Lessons on Physics. His new book, Helgoland, that will be discussed tonight, explores the quantum revolution at the beginning of the last century by analyzing with a fresh look the result struggles in interpreting quantum mechanics. His take is modern and different from other narrations that physicists made, such as the classical take of Gamow, the 30 years that shook physics, or the Faust in Copenhagen by Segre. And he will tell us tonight about this common problem encompassing most significant areas of contemporary physics, ranging from quantum gravity to particle physics and condensed matter physics. He will be in conversation with Katie Mack, theoretical cosmologist. She graduated in Princeton in 2009, and since then worked as a postdoctoral fellow at Kavli Institute for Cosmology. And in 2012 has been started an appointment as a DCRA fellow at the University of Melbourne. And in 2018, she has been, and since 2018, she has been an assistant professor at North Carolina State University. Her research interests are very varied. Particularly important highlights are her interest in dark matter, one of the most important problems that she investigates, and broadly speaking, the evolution of our cosmos. She has a phenomenal science outreach and a very broad footprint as a science communicator. She wrote in The Guardian, Scientific American, Time, Cosmos, and she has a very important presence on Twitter, and wrote a very nice book about possible scenarios for the end of our universe. I will stop here, and I'm looking forward to hearing from both of them tonight.
Thank you so much for that introduction. I'm really excited to be here. I'm really excited to talk with Carlo and about this truly amazing book that I've very much enjoyed reading. I think that Carlo, you have a little reading to start with. Maybe we can kick off doing a little excerpt.
Okay, I will. I do. Thank you very much. Katie, should I call you Astrokate?
Katie is fine.
No, Astrokate is much better. I mean, I guess as Astrokate is the most followed Twitter account in science, maybe, of all, certainly in physics.
Not exactly, but
nearly, or at least in physics. So I'm very grateful. Thank you for helping me talk about my book. Yeah, I want to read just a page and a half, no more than that, of my book. And just to put in context what I'm going to read. The book is about quantum mechanics. So there is entanglement, there is quantum interference, there is a Schrödinger cat, a wave, all this usual discussion about quantum mechanics, with an effort, which is what I usually try to do in my books, to go to the core of the problem and give a perspective, which is the perspective I look at these things, which seems the more interesting. But the book goes around that because it talks about the general cultural context that has led there to quantum theory, and that I believe helps us to, or might help us to frame the actual open problem of understanding what this incredible theory is telling us about the world. So I've chosen a page which is unusual in a book in quantum on quantum mechanics, because it is a little chapter that talks about a Buddhist monk and a Buddhist philosopher whose name is Nagarjuna, who is actually a major classic of Eastern philosophy. It's like Plato and Aristotle for the West, even if it's not very much known in the West. And I have a chapter in which I say something about his ideas and how some aspect of his ideas might help us to get some conceptual tools for sort of districating the fog around quantum theory. So here it is, the long search for the ultimate substance in physics has passed through matter, molecules, atoms, fields, elementary particles, etc., and has been shipwrecked in the relational complexity of quantum field theory and general relativity. Is it possible that a philosopher from ancient India can provide us with a conceptual tool which might help us to extricate ourselves? It is always from the others that we learn, from those different from ourselves. Despite millennia of an interrupted dialogue, the East and the West still have something to say to each other, as in the best marriages. One thing I remember early in the book is that Schrödinger was enamored and a deep reader of the Vedanta and his Schrödinger equation, his idea of waves. He often said he was inspired by that. The fascination of Nagarjuna goes beyond the question raised by contemporary physics. His perspective has something dazzling about it. Nagarjuna does not fall into the trap in which so much philosophy is caught by postulating starting points that invariably turn out to be unconvincing in the long run. He speaks about reality, about its complexity and comprehensibility, but he defends us from the conceptual trap of wanting to find it an ultimate foundation. His is not metaphysical extravagance, it's sobriety. It recognizes the fact that to inquire about the ultimate foundation of everything is to ask a question that perhaps simply does not make sense. I believe that one of the greatest mistakes that made by human beings is to want certainties when trying to understand something. The search for knowledge is not nourished by certainty. It is nourished by a radical absence of certainty. Thanks to the acute awareness of our ignorance, we are open to doubt and can continue to learn and to learn better. This has always been the strength of scientific thinking born of curiosity, revolt, change. There's no cardinal or final fixed point, philosophical or even methodological, with which to anchor the adventure of knowledge. There are many different interpretations of Nagarjuna text. What interests us is not what the prior of a monastery in India was actually thinking nearly 2,000 years ago. This is his business. What interests us is the power of the ideas that emanate today from the lines he left, and how these, enriched by generations of commentary, may open up new spaces for thought, intersect with our own culture and our knowledge. This is the meaning of culture, an endless dialogue that enriches us by feeding on experiences, knowledge, and above all, exchanges. I'm not a philosopher. I'm a physicist, a simple mechanics. And this simple mechanic who deals with quanta is taught by Nagarjuna that it is possible to think of the manifestation of objects without having to ask how the object is in itself, independent from its manifestations.
Thank you so much for that. That's a wonderful way of introducing this idea of relationality, which we will talk about in a little while. But I thought maybe we could go from this to describing the basic problem of quantum mechanics and what it is that you're tackling with all of this discussion, and what the big sort of unsolved mystery in quantum mechanics is, how it comes about.
I would describe it in this way, if I trying to summarize it. Quantum mechanics works very well. It's the basis of so much of our technology. So in terms of how we use it, how we apply it, and its effectiveness, it's just very good. But the way it works, it's like treating physical system like closed box, so to say. What the theory tell us is that if you do something and then wait a little bit, if you do something else, that's the way the system reacts back to us. This is presented in textbook by saying that it tells us what we observe when we observe a system. This is fine. We could do the same game with classical theory. But in classical theory, we have a story, what happens between one observation or the other. We see the particle here, and then we see here, and we can tell the story that it moved through this line. If we try to do the same in quantum theory, we get deeply confused. We have stories which take it seriously, don't make much more sense. Typically, we have an electron. We see it here, literally. I mean, we've proved that it is here at some time. And then we see it there at some later time, fine. And if we try to make a story of what happened in between, the electron opened up in a wave, went through all space, and then magically collapsed in a point. And the funny thing is that this is the way we're talked about the theory. The funny thing is that when is it that it collapsed in the point? When we look at it. So how does nature know that we are looking at it? Are we special? What's going on? Why is it observation? So there is taken literally, it works. But if you want to take it as a description of the world, it's just incomprehensible. So there are different attitudes. One is to just, ignore the problem. After all, you measure something, this is it, it's correct. You want to build a computer, you want to build a chip that works in the proper way. When the signal comes in, signal goes out, and the user theory tells you exactly what happened. So don't ask, don't say. But science gain when we ask questions, right? And many people find this attitude of don't ask, don't say unsatisfactory, and try to get a picture of what is actually going on when we don't observe, or understanding why is it that we coming it seem to make a difference. Observations seem to make a difference. And the possible answer are several, and are called interpretations of quantum mechanics in the jargon.
And this is a pretty big departure from classical theory, where we don't need interpretations. We can say, we know exactly what's happening from here to here, and there's no probability. We don't have to say we're going to do this experiment, and maybe 50% of the time we'll observe this, and 50% of the time we'll observe that. Quantum mechanics really is a totally different way of viewing the world, and gives you these strange you have to if you think you want to actually say what's happening, you're forced into these very weird corners, and exactly. You're gonna, I guess, say a little bit about what these interpretations are, and it's I think this is where people who are not working in physics encounter the utter weirdness of quantum mechanics, the idea that there are all these weird interpretations, and none of them seem to be compatible with the way that we think about the world.
Yeah, let me mention just two interpretations. I don't want to go through. In the book, I describe more of them, the one which are more discussed among physicists and among philosophers. Just mention one, two. Too extreme somehow. One is to think about the electron that opens up in a wave, and then we see in a point. One, which is called many-world interpretation, which is popular among some cosmologists and among some philosophers. Oxford philosophers love it. This is the idea that this wave in which things open up, it's a real stuff. The wave function that Schrödinger introduced, the psi, the quantum state, that's a real stuff. So the electron is really a wave, okay? But then the question is, well, wait a moment. If it is really a wave, how come that we don't see it all over? We only see it in a point. I mean, suppose we have many detectors, or we have a screen, okay? When the electron arrives on a screen, it arrives on a point. It's just there, not elsewhere. Well, these people who use this interpretation say, oh, well, yeah, no. The reason is that you, Katie, who are observing the electron, also are described by a wave, okay? So when you're observing the electron, your wave and the wave of the electron interact, so the electron is spread out, and as a result, you are going to spread out. So now you become a multiplicity of yourself. One that sees the electron here, one that sees the electron here, one that sees the electron here, one that sees the electron here. And they're all real. So you are just multiplied, and the world has split in a plurality of worlds. In each one of them, there is a Katie that sees a different electron somewhere. And now you're going to say, well, wait a minute, I am one, and I just see the electron in one point. And they say, sure, because you're one of them, okay? And that's why you see. Now, this is called now you think it's crazy. It is crazy, and but the people who believe in that, and I have good friends that believe in that, it's just not them who are crazy. It's the serious crazy. Somehow, whatever you do, it pushes you in something crazy. I don't think that that's the right direction to go. I think that's a multiplication of ourselves, which is in a sense it's an attempt to think that the world is really like we were in classical physics, one thing, this wave that goes all over, and it's not seeing that the wave is just a wave, a computational to see where the electron is going to show up next. The opposite kind of interpretation, that's another interpretation that recently people have looked into it, is to say, well, we don't know about the world, and we cannot describe the world. We cannot describe reality. The only thing we can say is that there is an agent, a human being, a mental something that can make observation and take notes and compute the future. And quantum mechanics is just telling us the best bet to see the next thing we're going to observe, ignoring what's going to happen out there. So it's sort of take science to total instrumentalism. We don't know what's going to happen, but we have a tool to give a probability, namely to bet at best what's going to be see after. Here, I think that we can do better than that. And but I want to stress that all these different interpretations of quantum mechanics, the main one can be maybe 4 or 5. Then there are variants of this and some particularly marginal ones, or they are all coherent. It's not that they're wrong. I mean, they've been debated, discussed. We could interpret nature in this or the other way. The question is that, is it useful? Does it make sense to think that there are copies of ourselves? Does it make sense to not ask questions of what happened there?
Yeah, I mean, I think that gets to, you know, the sort of basic way that I think about physics anyway, is when we're talking about theories, the whole point is to create something that's a useful model of the world and that will give us something to do. And whether or not we're really getting to ultimate reality, it's nice to think that we are getting to ultimate reality, that we are, you know, creating, you know, being able to interpret the world in a way that it actually is. But with these interpretations, it's not clear how much that actually is happening. I mean, the many worlds scenario, you get, you know, all these copies of yourself that you can't interact with, that do different things, and then sort of disappear from your perception immediately. And in the other situation, you have some aspect of reality that is completely opaque to you forever, and you'll never be able to observe anything. And you know, there are, as you mentioned, a few other interpretations, but it's a fascinating area because the data are very clear, right? You know, the equations all work extraordinarily well, and you know, the data are, we get the right answers for our experiments, no matter which of these interpretations we use. There's some limits to that, of course, but
no, you're right. If I may jump in with an observation, that's right. We cannot distinguish empirically, at least between these two interpretations and the relational interpretation, which I defend in the book. But science is not just about things that you can distinguish empirically. Let me make an example. When there was a Copernican revolution, a big discussion that followed from that is whether the Earth is the center of the universe, right? Mm-hmm. Now, if you think for a moment, the question is not empirically well defined. I mean, how do you check whether the Earth is the center of the universe, right? We have absolutely no way to know whether So one may say, oh, that's a philosophical question. It has no meaning. Oh, well, wait a minute. It had an immense meaning, and it drove science in the right direction by moving our understanding from the Earth is the center of the universe to, no, the Earth is not the center of the universe. So we reframed the conceptual structure in a different way, which allowed Newton, Huygens, Kepler, and so on, to develop mechanics and so on, and go ahead. So Feynman had a beautiful way. I love the way Feynman put it. He said, nature has a remarkable capacity that can be interpreted in different ways. A good theoretical physicist keeps 5 or 6 different interpretations of the same phenomena in his mind. Okay, and so far it seems, well, they're all equal. They are not, you know, why choosing one? Now, because Feynman goes ahead and said, because a good theoretical physicist keeps all in mind because he doesn't know the one which is really going to be useful next. So they are not equal. One is going to help you to think better. So
Right.
I think that, like, you know, the Earth is the center of the world, with quantum mechanics, slowly we'll figure out that one way of thinking takes us ahead.
And you put out a very good argument in the book for one particular interpretation that is separate from the two you mentioned.
Yeah.
Do you want to talk a little bit about that one?
Yeah, it's called the relational interpretation. It was born in the 90s, and it has been slowly clarified and grown, and has got the interest of the philosophers first, different kind of philosophers, and then more physicists. And in recent days, it's discussed much more. It's called the relational interpretation. And the idea is that forget the wave function. I mean, the electron is not the wave function. It's not a function. The electron is it's a particle which has a position and has some properties. However, how do you make this consistent with experiments and with the mathematics of quantum theory? The main idea is the following: that the properties of an object are not something which is in the object, inherent in the object, as something that describe the way the object interact with something else. So they only are relative to the interacting things, and they only make sense when in the moment of the interaction. So literally, the electron is something which has no position unless when it's hitting something, when interacting something, and its position is relative to whatever is interacting with. So it's a weakening of the sort of realist picture of the world in which you have object with properties. You know, in classical physics, we describe the world in physical systems, and each system has always some properties which describe with variables, and we have equations for these variables. Quantum mechanics does not give us how these variables evolve in time always. It only tells us how these variables manifest themselves from one interaction to the next one. So it gives the probability amplitude from one to the other. And if you reinterpret properties in this way, namely as relational, not as property of a single object, you come out of the confusion of the puzzle of quantum mechanics. Somehow it works for let me give you an example. There's a famous situation in which the state, the wave function of a cat, Schrödinger cat, Schrödinger says it can have two components, one with a dead cat and one a live cat. In my book, I prefer a sleeping cat and a wake cat because I don't like joking with dead cats. So the state, the wave function has both. And the mystery is, what does it mean? I mean, suppose you are the cat. I mean, can you feel yourself being two things at the same time? And I think the answer is no, because the right attitude is that they're not both. With respect to an external object or things, which is outside the box in which the cat is neither awake nor asleep, because there's no interaction going on. So there's nothing to say about the cat. But with respect to the cat itself, it's just one of the two. And the point is that the fact that with respect to the cat itself is just one of the two does not necessarily affect what the external observer might observe. So he's not going to erase the quantum interference between the two branches. So that's a key. And if we accept this relational interpretation of properties, quantum mechanics, I think makes sense.
Yeah, I found this a really fascinating way to think about it, partially because one of the things that it does is it removes the possibility of a sort of objective God's eye view of the universe, and everything is inherently subjective in a kind of similar way to how it is with relativity, where simultaneity is broken. Something might seem to happen at the same time to one person and different times to someone else, depending on how they're moving and their situation. And similarly, there can be a cat in a superposition to me, but to the cat, it's clearly one or the other. But there's no contradiction there. But does that? So you talk about it a little bit in the book. How does this change how you think about the world if there's no objective thing that everybody agrees on, but it's really about the connections between observers, the connections between physical objects, how everything's relating to everything else?
Let me first give you a precise scientific answer, and then a more vague answer. The more precise scientific answer is that once we take the theory and we study exactly what is telling us the theory, we see that these discrepancies between what different observers see turn out to be very little and turn out to be rapidly invisible as soon as there are many degrees of freedom. Technically, it's decoherence is called. It's a well-understood phenomenon for which the quantum interference, which is the ringing bell that tells us, careful, look, I mean, properties are relational or not absolute. You have to take into account the other branch of the wave function. But quantum interference becomes invisible as soon as you have many degrees of freedom that you cannot check them. So as soon as you have big things, let me say naively macroscopic things, the difference between the way you see the world and the way I see the world disappears. So properties become, you can forget that they're relative. You can just forget the label. So you don't see them. And so largely the world we see is the same. It's not that each one of us sees a different world. Each one of us sees a different world if we go very careful to the point of measuring quantum interference, quantum properties, quantum behavior. But to measure these things, you have to isolate things. To be very, I mean, quantum systems are solitary systems. Matteo, who introduced us, who works in a laboratory, I think knows very well that to have a quantum phenomenon come out, you have to isolate the system. As soon as your system is not isolated, quantum phenomena disappear. That's why it's so hard to do quantum computing, quantum computers. And then, of course, there is the fact that there are approximations. You worked in cosmology, among many other things you worked on, and you wrote this fantastic booklet about the end of the universe, right? And when you talk about the end of the universe, I mean, what's going to happen to the universe in the distant future? Are you really talking about everything? And of course not. You're talking about a sort of an average, the large degrees of freedom of the universe. Cosmology is not about everything. It's about a very fuzzy way of viewing things in which you don't see the details. So is a dramatic approximation, right? It's like when the physicists say a cow is a round thing. So of course, then the more you approximate, the more things are well defined. And so we can talk about the usual reality as usual, and the strangeness only comes in the details. So that's a scientific answer. But then I want to add another answer, which maybe opens a different discussion, but let me just mention it. Relationality is not something which is strange when I was thinking. We're used to relational thinking. In our daily life, we say that brother is a brother because there's another brother. I mean, we say chemistry is about relations. Chemical properties means not the property of the thing, it's how it interact with other chemical elements, and so on and so forth. So relationality is not strange. We think in terms of relations. The surprise here is that quantum mechanics telling in some sense that it's relations all the way down.
Right. And even at the fundamental level, nothing is defined independently. It's all about how it's interacting with everything else.
Exactly. Yeah. That's the central point.
Right. Yeah, so one of the things that comes up in the sort of closing chapters of the book is sort of the implications of this for other aspects of thinking about the world, and one of the ones you go into is the nature of consciousness, and this is something that that you see fairly often, physicists and cosmologists delving into this question of what does it mean to be conscious, what is, how does this connect to physics in some way. Can you tell me a little bit about what drew you to that question, and how that connects with these ideas?
Yes, the reason the reason physicists are driven to these questions, not all of them, some just don't care about, but several, is that of course, physics cannot be used to understand everything, obviously, right? Physics has its own methods, and I mean, you don't understand a complicated protein just in terms of physics. You use chemistry, use biochemistry, use the notion there. As I write in the book, I mean, knowing that my girlfriend is follows the Maxwell equation doesn't help me to make her happy. But I know that she follows the Maxwell equations, and it's just useless notion in a way. So I know that she follows the Maxwell equation. So physics has a super general applicability. I mean, biology does not apply to a stone, and chemistry does not apply to a single proton. Physics, as far as we know, applies to all the things we know, and we don't see any a priori problem to the fact that complicated things, in principle, even if not in practice, I could apply physics to it. But then consciousness is constantly put forward by people as an example of something which seems to escape this idea that, everything follows physics. In a confused way, because what people mean by consciousness is vague, is not clear what is, so the subjective perspective or whatever. So that's why physicists, I think, because they feel that there is somebody saying, oh, this is outside physics. Not outside physics in the sense in which, a thunderstorm is outside physics because you need other stuff to understand it. It's outside physics a priori, breaks the laws of physics, outside the laws of physics. And so physicists say, wait a minute, how is this possible? And I think, so it's a philosophical point of view, is that naturalism, in which I believe we as human beings are part of nature, just a piece of nature like any other. Is this contradicted by the phenomenon of consciousness? So that's the reason of the interest. I think that quantum mechanics has, strictly speaking, nothing to do with that, because I don't think that in our brain, or that I think consciousness, it's whatever it is, it depends on, we're going to understand it by understanding how our brain works, how are the neurons and the chemistry and the biochemistry and everything, what's happening in the computation of our brain, all these things together in some way. And nothing of that is really quantum mechanical, specifically quantum mechanical. However, I think that quantum mechanics helps us to heal from a misconception that creates a problem. And the misconception is the following. The problem of consciousness comes from the idea that there's one entity, which is me. Me, the subject that sees. This is an entity. And then there is nature made by little stones bouncing around, pushed by force. And if you formulate the problem in these terms, oh my God, how can, stones bouncing around generate something which is me seeing around? And I think the relational thinking of quantum mechanics pushes us not to understand how the brain works, of course, that's jobs of the neuroscientists, but pushes us to get rid of this silly picture in which there is me as an entity and nature as stones, because me as an entity doesn't exist. I am a complicated set of phenomena, and that nature is not made by stones each one with a position and velocity. It's much more complicated. It's made by relations between systems that affect one another. So if you make these 2 steps back, you realize that the way physical nature works is much more complicated, that the naive materialism was just 18th century materialism was just stones bouncing around. And that me as an entity, it's not me as an entity, it's a result, it's my awareness, it's a little bit of a complicated phenomenology which I don't control, that happens in my brain. Then the separation between the mental and the physical becomes much less dramatic, and it's not that you resolved it, but you think, well, yeah, if we study enough, we can understand one in terms of the other.
Right. Yeah. Thanks for that. I think we are at the time now where we will be answering some questions from the audience, things that have been submitted. So I'm gonna choose some somewhat arbitrarily. So if your question doesn't get answered, I apologize in advance. But the first one that I noticed that I thought you might find interesting. The question is from Richard Johnson. Is time itself a fiction, just a matter of counting events like ticks on a clock? Are we really measuring anything real?
Well, it's both. And this is the entire topic of my previous book, which is all about what is time. And the thesis of that book, I mean, I spent half of my life studying time because I do quantum gravity. To do quantum gravity, you have to understand 2 things. What is quantum? And that's why I wrote Helgoland. And what is time and space? And
right.
That's why I wrote previous book. So the story about time is that there isn't just one thing which is time. We call time different things. So we call time the sequence of events, okay? And one thing happened, and then the other one, and then the other one, and the counting of this, we call it time. So that exists. It's there. It's one aspect of time. But that's not Newtonian time, because Newtonian time is something else. Newtonian time passes even if nothing happens. Okay, and Newtonian time, it's a different notion of time, which in fact was introduced by Newton, which has evolved into the Minkowski space-time, this geometrical structure in which everything, the rest happens, which has evolved, and we understand it better. We have understood what it is slowly, into the space-time of general relativity, which is, that's Einstein's great discovery, the gravitational field. And the gravitational field is like the electric field, the magnetic field. So it's stuff, it's an entity. So what is a clock measuring? It is measuring something. Yes, it is in general relativity. If you write the dynamical equation of a clock, you see that it's measuring something. It's into the integral, the line integral of G mu nu along a line. So it's measuring a property of this field. Mm-hmm. So by time, we mean the measure of this gravitational field along this line. So it's actually a thing, a real thing. So much that in quantum mechanics, it becomes quantized. It's a stuff like the photons or stuff. So yes, it's a thing, but we also use a much wider notion of time in our everyday life, which doesn't necessarily connect to that one, which is just the counting of events. So these kind of questions are always need to be answered by breaking up the concept, in this case, the concept of time, and realizing that we use it in different meanings. They're all good in their context.
Right, right. There's another question here by an anonymous attendee, and I think I know how you're going to answer it, and I'm going to ask it because of that. The question is, what does quantum theory say about parapsychology?
Okay. It says a lot. It says really a lot. It said, just forget that's bullshit.
Okay.
Let me put it stronger.
Okay.
There is a lot of quantum stuff out there in our world, in the internet. Just go in the internet and look for quantum psychology, quantum motivation or parapsychological things, quantum medicine, quantum exercises. There's quantum little things that you buy, you put it here and you heal your, okay, stay away all nonsenses. This is just crap, and it's just to take money from the naive and stupid people.
Yeah, I there's one of the parts of your book that I really appreciated was the bit where you expound on how dangerous it can be to blame quantum mechanics on blame quantum mechanics for a number of ailments or psychological things or whatever. And so anyway, thank you for that very strong statement.
I get mail saying, you know, I had a strange feeling that was I was living again an experience of time ago. Is that a quantum mechanical phenomenon? No, it's not. For sure, nothing to do with quantum mechanics.
Yeah, quantum mechanics doesn't mean you can just let anything ever happen. It doesn't mean you can just throw out everything you know about the world. It's anyway.
That's right.
Okay, there's another question here. What is an experiment that could support the relational interpretation over others?
There is none. There isn't any. So far, the situation is strongly that the majority of the interpretation of quantum mechanics are empirically equivalent. There's some attempts to sort of solve the problem by saying, well, quantum mechanics is strictly wrong. We have to tweak with it, change it, and then it can be tested. But the one we mentioned, the relational quantum mechanics and cubism and many worlds are all empirically equivalent. There are some papers out there that make some claims that, oh, this supports this interpretation of the other. There are some papers that says, look, this, like in relational quantum mechanics, this experiment proves that facts are relative to the observer. Yes, it's true. I mean, this is an interpretation. This is something done in the lab. In fact, there's some beautiful experiment, by the way. There's some experiment that sort of make a sort of Schrödinger cat for real. I mean, there is a part of the experiment of the apparatus that measures something else, and then you see that from the outside you get something contradictory, which was measuring from the inside, and it seems to be saying, oh, look, this is exactly what relational quantum mechanics says. Yeah, true, but this is because you're looking from these lenses. If you are a strong believer in the many worlds, you look through different lenses and you give a different story of what goes on, and it's equally, you give an account of what goes on, which fits with what ultimately you're going to observe yourself. And so it might be that some experiments are more easily thought in one way or the other, but they're not decided in any manner.
Okay, yeah. There's another question, and it relates to something I was maybe going to ask you about as well, about your writing and the sort of beautiful prose that you use and how you talk about physics. But the question here specifically says, you write poetically about physics and quote poets like Dante and Horace in your work. Can you talk about the relationship you see between quantum physics and poetry? And this is signed by someone who is a poet married to a physicist.
Oh, maybe they should tell us more about poetry and physics. Look, I don't think I write in a poetical way. I just write what comes natural to me. The nice words are not meant, I mean, sometimes yes, but rarely, mostly are not meant to embellish a presentation. Is that I think that, as you were saying, Katie, at the beginning, science is not about, writing a number, doing some mathematics, and then going to an experimentalist who gives us the result 42 and you check it's the right number. That's not what science is. Science is about developing a picture of reality. Mm-hmm. And you don't need this to be the ultimate picture. You want it to get a good picture, good as far as we know today, so that we perhaps tomorrow we can get an even better picture. So I think that this conceptual, visual, understanding what's going on thing, it's important. But precisely because science is so often forces us to abandon previous notions, we're always lacking words for saying what we've been understanding. So in a sense. So my books like Helgoland or The Order of Time, they're written not like many other books to give all the details, but to try to zoom on a main idea and try to clarify the main idea.
Carlo, your
sorry,
video seems to have
I
stopped.
disappeared.
Yeah.
Okay, yeah.
Yeah, thank you.
Here it is. And I try to be as clear as possible about one central idea of some deep theory, like, you know, general relativity or quantum theory, or some deep theory we're trying to build up, like blue quantum gravity. And for that, it's a search for words that helps us to jump out from usual way of thinking and get a new way of thinking. And in that sense, physics is not very different from poetry, even if, you know, the tools are completely different. But you're trying to say something which is hard to say, and to create new meaning, new language for expressing something. So science is a way of viewing reality differently, and poetry is a way of viewing the reality differently. So with all the immense diversity of tools and aims, there is some common long-term aim, which is open our eyes to a different perspective on reality. Plus, they're both ultimately dominated by our passion, right?
Yeah.
You want to know how the universe is going to end.
Yeah.
Because that interests us, because that's a passionate thing to know. Not just because you're a cold rationalist that among all the questions, you know, I mean, who cares about cold rationalists?
Right. Yeah, I mean, yeah, for me, I think when I write about a subject in physics, I try really hard to find the right words, because I want to get my enthusiasm out there. I want to share my passion, and I want the idea to affect the reader emotionally the way it affects me.
Yeah.
And I definitely can perceive that in your writing, and it's amazingly effective at doing that. Can you just say, just briefly, like, I mean, I have my own reasons for writing for the public about you know, complex physics theory. What is it that, aside from just wanting to share your excitement or passion, why is it important to talk about these topics in a way that people can understand?
I started very late in writing for the larger public. In fact, in my 50s. Before I didn't even think about. People ask me, I mean, you're doing quantum gravity, or you look quantum gravity, why don't you write a book about that? I thought that you know, I had to do science first, I don't know, something like that. Then a little bit the opportunity opens up, and somehow, you know, things leading to things took me there without big decision. But I guess my first book was the Reality is Not What It Seems. It was really a sense of it's so beautiful what we're doing. It's so relevant. It's so extraordinary. It's so magic that I'm surprised if at least some people out there don't want to know about that, right? It's just having a little jewel in your hands, and, you know, just talking with your friends, and they say, well, let's show that to everybody. It's just so beautiful. Look, there is marvel, there is astonishment, there is I think it's important. Not important. I mean, people can be interested in that or not. That's what they want. But why keeping it hidden?
Right. Yeah. No, I agree. I think that you know, part of what we have the ability and privilege to do is to share this with people and allow them to have that amazing feeling of understanding and connection to their universe.
To the understanding, connection, universe, and connection to the open questions, right? Like the things we don't know and we are trying to see, and our knowledge and our lack of knowledge and boundary, and our advancing toward little bits more of knowledge.
Yeah. So I think that we probably have time for only one more question, and there are so many questions, and some of them are very detailed, and I really apologize to everybody who we don't have time to answer these questions. But let's see. So for the last one, okay, the question is, do you have any hopes or concerns for future physicists / the field of physics? How do you think about the future of physics?
I'm optimistic. And I'm aware that recently, some time ago, there have been some claims, oh my God, physics is in crisis. People have screamed in a crisis. For instance, when supersymmetry was not found at LHC, some said, oh my God, physics is in a crisis. Physics is certainly not in a crisis. I mean, it's some research directions are in a crisis.
Right.
I mean, a lot of physicists never expected supersymmetry at LHC, and so they are very happy that their expectations were confirmed. In fundamental physics, there have been an extraordinary capacity of the people of the last century, who has put together general relativity on the one hand and the standard model on the other hand, that works so incredibly well that somehow the crisis that they've been so good that it keeps being keeps being right. But first of all, there are obviously open problems there, quantum gravity being one. And we're learning enormously about the world, and cosmology is an example in which we are learning so much about the universe we just didn't know 10 years ago. I mean, just think about black holes. I mean, now we know that there are black holes all over. Also, we have pictures of black hole with the gravitational waves. We have wow. When I was hired in France 20 years ago, the director of the lab, who's a very serious physicist, asked me, well, Carlo, you don't really believe that black holes are for real out there in the sky, right? So that was 20 years ago. He was a very good physicist, but many physicists didn't expect. So we are learning about the universe enormously still. And I'm sure that it's going to continue if humankind is not so stupid, to kill one another with another war and, stupid things like that, destroy the planet as we're doing, fighting China with America and all these stupid, idiotic things which are going on.
Well, on that hopeful note, let's. I think we can wrap up. I'm not sure if Lauren will come back and sort of round us out.
Thank you. Thank you so much, Carlo and Katie, for that beautiful, thoughtful conversation. Thank you, Matteo, for that excellent introduction. And thank you to all of you. I'm sorry we didn't have time to get to all of your incredible questions, but thank you so much for spending your evening with us. Please check out Helgoland and purchase copies at harvard.com. And on behalf of Harvard Bookstore, the Harvard University Division of Science, and the Harvard Library, all here in Cambridge, Massachusetts, thank you so much. Have a great night. Keep reading and please be well. Thank you all.
Thank you, Matteo. I would have liked to know more your thoughts on quantum theory. Thank you to the Harvard Bookstore, but especially thank you to Katie. You've been extremely generous for that. Thank you very much to everybody.
Thank you. It was really a pleasure. Thanks, everyone.
Have a good night.